Okay, so I'm going to be moving on with my Griffiths problems. I did 1.7 last time, so now I'm going to do 1.8. This one's pretty short and sweet. Now this is still after section 1.4, so this is all about normalization. And I did go ahead and I did have a video on YouTube about normalization, and that's Griffiths section 1.4. So that's what all these problems are about, and that's about making sure that our probability of finding the particle in all space, so if we take our probability density function, which is our wave function, the absolute value of our wave function squared, the probability of finding it anywhere in space has to be 100%. We need to have a 100% chance of finding our particle somewhere. It has to be somewhere. It's a real physical particle. So we are going to normalize it so that it has a 100% chance of being found and we don't get any weird numbers. Now, we have part 1 is normalize and then determine the expectation values, and then it talks about standard deviation, and then it has sketch. I like to always start with a sketch. I just find it's very useful to get an idea of what my function looks like. So if I have, just psi and x, I'm going to go ahead and just look at some values for this. So my wave function is a function of x, and it is also a function of time, t. But as we found out in our Griffiths section 1.4, if I normalize a wave function for any value of t, it stays normalized. So I can normalize it at t equals 0 because that's the easiest one to do. And why, if we can do any t we want, why not do the easiest one? So this is our normalization constant a. At x equal to 0, e to the 0, anything raised to the 0 power is just going to equal 1. So at x equals 0, my wave function just equals a. Then as I increase x, I put in positive values for x, I have an exponential decay, which I'm not really good at drawing, so I'm just gonna, do that. So it's decaying. This is also a condition that we have for our Schrodinger equation puts on these wave functions, is that they have to be converging. So I can't have something that blows up at infinity. I can't have a diverging integral. All of my integrals have to be converging, so that's a decay. If I plug in negative values for x, well, my x is surrounded by absolute value sign, so what I have here is a symmetric function. At x equals infinity, then that's just going to go to 0. So e to the negative infinity is 0. E to the negative infinity is just 1 over e to the infinity. And we get the same thing on the left side too. We get e to the negative infinity, and 1 over infinity is 0. So it converges. So we're happy. So I did part of C. Now I'm going to go back to A and actually do the first part, which is to actually normalize it. So I set my probability over all space equal to 1, and then I'm going to integrate over all space. And then I have my wave function squared, so that's going to be a squared e to the negative 2 lambda absolute value of x. Now, as we see here, this function is symmetric about the 0 axis, and whatever is over here is the same as over here. So I'm just going to simplify that up a bit, and instead of doing my integral from negative infinity to positive infinity, I'm going to just do it from 0 to infinity and multiply the result by 2. This is a pretty easy integral to do. We just have 2 times a squared from 0 to infinity dx e to the negative 2 lambda x. E to the x is probably the easiest integral. I think that's a pretty fair statement to say. And then we just have, the like the derivative of the inside times the derivative of the outside. So I get 2a squared. Then I'm going to have 1 over negative 2 lambda, because that needs to be pulled out. And then e to the 2 lambda x evaluated 0 and infinity. So if I took this derivative, I would get negative 2 lambda divided by negative 2 lambda, so I would just get returned my original function back. I can go ahead and evaluate that. So e to the 0 is just 1. E to negative infinity is 0. So we're just going to get, and then our 2's are going to cancel, and we just get a squared over lambda. I solve that for a, and I get that a is the square root of lambda. So now my normalized wave function is going to be psi. I can even be fancy, put in my t back. So my normalized wave function is square root of lambda, e to the negative lambda x, and then e to the negative I omega t. Okay, so that's part A. That's pretty easy, pretty straightforward. Generally normalization is kind of fun. It's nice and straightforward. Don't have to worry too much about it, especially when you have like these plane waves, these exponential functions. Okay, now we want to find the expectation values. We want to find x and the expectation value of x squared. The reason we want to find those is so that we can then find the standard deviation later. And the next section of Griffiths is going to be all about expectation values, so we can find out more about it there. Now, the first one, so in general, my expectation value is going to be just the general integral, and it's going to be psi x psi complex conjugate. Now in this case, since I sketched out my function, I know that my function is even, right? It's symmetric about the x-axis, and because it was even, I was able to do that shortcut with my integral, where I was able to change those limits from, so instead of integrating from 0 to, or from negative infinity to positive infinity, I was instead able to just integrate from 0 to infinity and double my result. So now, so I have a, and then this guy, so the guy needs to be squared. But now we have it multiplied by an x. And x alone is odd. So if I sketch out, I have some exponential decay times some linear function, whatever that looks like. The thing is that now on the other side I have the exact same thing, but now it's times the opposite of whatever that is. So whatever I had over here, I have over here, but opposite. My function's now odd. So that means whatever is on this side is opposite of whatever is on this side. So I don't even really have to bother with it. I can just set it to 0 because it's odd, and I'm integrating over all space. So that was pretty easy. Yeah, my expectation value of x is just 0. So that would be at x equals 0. Now let's do this guy. So x squared is going to be, and we have from negative infinity to positive infinity, dx lambda e to the negative 2 lambda positive x squared. Now x squared is also even, so that's good news for us. We can go ahead and simplify this out and handily get rid of those absolute value signs. 2 times lambda x. Okay, so now this one, I believe I just looked this up in an integral table before, but I'm going to go back to the solution I did before of this guy, which was a while ago. Oh, I guess I did the whole x equals 0 by integrating by parts. Yeah, I looked it up in an integral table. I was lazy. So that's x to the n, and then we have n factorial over a to the n plus 1. That's usually how I do integrals instead of working them all out by hand anymore. I'm trying to get better at going over the basics again, because it's been so long since I've done the basics. N factorial over a to the n plus 1, which makes sense. I just don't want to integrate by parts twice, I guess. Is it just being lazy? Okay. And you see how it's handy since it's even. This is just simpler to do because then I can plug in 0 for my exponential and that just turns into a 1, and my other limit just gives me a 0 instead of trying to deal with the negative infinity and positive infinity. Okay, so then I get a 2 lambda, and now I get a 2 factorial over a, which is 2 lambda, 2 times lambda, and those are both going to be raised to the n plus 1. I think that was n minus 1. We're going to go back and check. Let's see. Oh no, it was n plus 1. Yeah, I guess. Oh, yeah, it did work out. I get I just get a squared power. Okay, so that's 3. And 2 factorial, 2 times 1 is 1. Or sorry, 2 times 1 is 2. And then that guy's gonna cancel out. So I get 2 lambda. That's one of those is totally gonna cancel. 2 over 4 lambda squared, and that equals 1 over 2 lambda squared. And that's what we get for our expectation value of x squared. 1/2 times 1 over lambda squared. Okay, so that's what we got for b. This is equal to 0, which is very handy. And expectation value of x squared is 1 over 2 lambda squared. And that's it for part B. Part C, we'll go ahead and grab a new page for that. So part C, we're going to be looking at, doing our sketch again. Although specifically it wants to sketch the probability density function, which isn't really, as far as I'm concerned, it's basically the same picture, right? Except that my peak here, instead of being just a, my peak is going to be a squared, so that's just going to be equal to lambda. And then that's psi, and then I'm just going to keep it at time equals 0. So that's negative lambda x, and then my psi squared is lambda e to the negative 2 lambda times absolute value of x. Basically same shape, at least as far as I'm concerned. Now, first we want to find the standard deviation. So our standard deviation is x squared, our standard deviation squared equals the expectation value of x squared minus the expectation value of x squared. That one, the first one was 0, and the second one was 1 over 2 lambda squared. Though I should actually, it's been a little while since I did this one, so I should probably go ahead and double check that. And here we have it on Griffiths, so yeah, I actually did get it right, which is surprising. Oh, I swapped them. There we go. There we go. Okay. And then I take the square root of that. So what I have is that my sigma is 1 over square root of 2 times lambda. So we have our nice sketch here, and I want to mark the points, this and this. So that's going to be 1 over square root of 2 lambda. I shouldn't be so picky, we're not doing this to scale. And then we have negative 1 over square root of 2 lambda. And this gives you an idea of what the spread is. So this is one standard deviation, this is another standard deviation. So that basically means that we have about a 2/3 probability of our particle being within one standard deviation. of the expectation value of x. But we can go ahead and figure out what is the probability that this particle will be found outside this range. So for that, we're just going to go ahead and integrate. So I'm going to integrate the probability density function from this point, from a standard deviation to infinity. And then whatever my probability is here, it's the exact same over here. So I'm just going to take my result from this, gone to x equals infinity, I'm just going to double it. So that's going to go, well, not from 0, because I'm starting from my standard deviation. So my first limit of integration is 1 over square root of 2 over lambda to infinity dx, and then I have my probability density function is this guy. I'm only considering the positive x, so I don't need the absolute value sign anymore. I have 2 times lambda out in front. Here's my limit, other limit, and I get dx e to the negative 2 times x, negative 2 lambda times x. My integral of that, pretty straightforward. It's just going to be 1 over negative 2 lambda times itself. So we have that constant inside the exponential does need to be pulled out. And then my limits of integration are this and infinity. This one plugged in is just going to equal 0. That's going to cancel that. So what I'm going to get is e to the negative 2 times lambda, and then over square root of 2 times lambda. My lambdas cancel out, so I just get e to the negative square root of 2. And I'm sure that equals a number. So that is our probability of finding the particle outside of a standard deviation away from the expectation value of x. I normalized it at t equals 0, but that's fine. If it's normalized for t equals 0, it's normalized for all time. And there we go. That is Griffiths problem 1.8. Very, very straightforward example of this first step of dealing with any wave function is always going to be to normalize it.